Hello class! Welcome to our Crash Course 2 and here we are going to discuss stereochemistry. Remember class, ang stereochemistry from your undergrad, this is a really complex topic. So for our discussion here, I will emphasize those high-yield concepts that you really need to study because they will be your core knowledge for our stereochemistry discussion. Okay? So here in our Crash Course 2, we will start with stereochem and under this discussion or topic, we have the intro, the requirements to make your compound chiral, the specific chirality, and lastly, the different specification of configuration. So without further ado class, let's start our Crash Course 2 discussion. So for our quick question, similar 4 picks, 1 word. For your class, I have 1 item. And of course, very obvious, ang common theme, diba? So you can pause the video in order to guess what is the common theme here in our first item. Class, very easy lang yan. That's your chiral compound, diba? They are non-superimposable mirror images of each other. And that will be our topic for this second set of topics under Crash Course 2. Let's start with our brief overview of stereochemistry. Class, when we say stereochemistry, we are now going to discuss the 3D structure of your molecule. Oh, sir, are we going to use the 3D representations, primarily your dash wedge line structure? Tama po. Okay? So again, to formally define, stereochemistry is the 3-dimensional structure of a molecule. And remember, this is very important. The stereochem, or we also call it your molecular handedness, diba? So this is important in orchem and of course in your biological system. So it arises primarily because of the consequence that your carbon, particularly sp3 hybridized carbons, emphasis on this, are tetrahedral in terms of its geometry or stereochemistry. Class, I would like to point out, stereochemistry is just exclusive for our sp3 hybridized carbons. And of course, stereochem has a lot of applications. For instance, many drugs and of course your biomolecules in our bodies, amino acids, carbs, lipids, nucleic acids, and so on and so forth, they are handed. They have a preference in terms of their configuration. Diba? Remember, we have your R versus S configuration primarily. So aside from that, stereochemistry, when we say they are stereoisomers, diba? So again, they have the same molecular formula, but check, they differ on how they are arranged spatially. Okay, so again, this difference in arrangement can actually lead to distinct physical and chemical properties of each stereoisomer. So again, the 3D structure of your molecule can impact, firstly, reactivity. So remember class, the molecular handedness can influence how our molecules or organic molecules in particular can interact with each other. Secondly, in pharmaceuticals, remember, many drugs are chiral. Okay, they exist as enantiomer. And of course, when you change the configuration somehow, their functions will also change. Diba? So remember again, sa pharma, we use mainly the concept of stereoisomerism. Thirdly, in your biological systems, we actually have a preference in terms of our biomolecules. For instance, diba? For your carbohydrates, ang naturally occurring forms, D configurations. For amino acid, that's the L configuration. Class, again, let's just focus on orchem. So lastly, we have your material science application. Remember, the physical properties of your organic materials, including melting points, boiling points, your optical activity, or the capability to rotate pink polarized light, can be influenced by stereochemistry. Diba, class? For your isomers, we can categorize it based on 2 categories. The first one, we already discussed it during our discussion on Intro to Organic Chemistry. Remember, that's one of the properties of your carbon. It can form constitutional isomers, particularly via branching of our linear hydrocarbon chain. Alright? And secondly, stereoisomers, this will be our topic for this session. Remember, class, we can predict the number of stereoisomers if we know the number of chiral centers of a certain organic compound. Sir, I know there's a formula for that. What is the formula nga po ulit? That's your 2 raised to n, where n is equivalent to the number of chiral centers present in our organic compounds. And particularly class, your stereoisomers can be further subdivided into enantiomers and diastereomers. So we will discuss this, don't worry. But for now, let's just focus first on our constitutional, or we also call it your structural isomerism. Remember, I already discussed this in our properties of carbon. For your constitutional isomers, let's take butane as an example. Remember, what is the condensed formula of butane or the molecular formula? C4H10. Check. Molenstick model for your linear chain. This is your butane. For its branching isomer, again class, it has 1 branching isomer and this is the structure of its isomer. Remember, this is a type of constitutional isomerism. So another example is with our pentane molecule. Diba? Remember, we have your pentane, isopentane, and neopentane. Oh sir, can you recall the structures of these 3 isomers of pentane? Yes. Firstly, we have your linear chain. Well, this is just your pentane class. Diba? Remember, we already discussed this. Second, class, this is your isopentane because we have branching in its structure. And lastly, the highly branched constitutional isomer of pentane, we have your neopentane. Again, we have a quaternary carbon directly bonded to 4 different carbon groups. Alright? So I hope it's clear for constitutional isomers, they have different attachment in your structure ng organic compounds. For your stereoisomers, they have different arrangement spatially. Okay? This is a 3D conformation or structure of your organic compounds. Ayan. So let's discuss our second topic. Diba? Speed lang for your stereochemistry discussion. Class, for stereochem, remember, we have the term chirality. When we say that a molecule is chiral, of course, this is a geometric property of your molecules wherein, as you can see, diba? Your structure is superimposable on its mirror image. Okay, so it's like your left and right hands, diba? So of course, meron tayong requirements for chirality. First one, we should have the chiral center. So your chiral center class, again, that's just synonymous with your stereogenic center. Your carbon here, remember, it should be sp3 hybridized. So that means it is singly bonded to 4 different functional groups, and therefore, in terms of its molecular geom, it is tetrahedral. Diba? So again, for chiral center, that's our non-negotiables. Ayan. Again, for the symbols, we usually use your asterisk here. Okay? In order to denote that a certain carbon or a typical carbon is a chiral center. Class, chiral molecules always have at least one chiral center, like this one. So usually carbon yan most of the time. And they should lack internal symmetry. Once they possess internal symmetry, it cannot be chiral. Okay, we call this your achiral compound. Let's now discuss the different stereoisomers starting with your enantiomers. Diba, very familiar na tayo with enantiomeric forms. So they exist in pairs because these are pair of stereoisomers that are chiral. Familiar with your R versus S configuration. So again, enantiomers, they have the same physical properties. Again, melting point, boiling point, except that they rotate plane polarized light in opposite direction. One going to the right, and then one going to the left. Class, typical example. So here we have your drug, S-naproxen. The usual, okay, the specific S-naproxen acts as an anti-inflammatory agent that we intake. Ayan. And it's our configuration counterpart. See, it's actually a liver toxin, the opposite of your, the advantage of our S-naproxen mechanism. Class, remember, this is very crucial. The configuration can really impact, okay, the activity and functions of our organic compounds. Sir, question. I know we also have a term, dextro and levo. What is the difference between these two? Class, again, for R and S, this is through our analysis ng 3D structure of your molecule. For instance, of course, we have your R and S based on your CIP rules or your Kahn-Ingold Prelog rules. Remember, we will discuss this also in our discussion here. But for now, for your D or L, remember, this is different with your dextro or levo. For this one, this is the physical property wherein we determine the rotation of your plane polarized light. Class, again, this is dextro and levo, not your D or L that we typically use. Remember, this is based on polarimetry experiments. Clear? Ayan, again, for our enantiomeric pairs, we have your stereoisomers that are mirror images. So let's take threonine as our main example here. So threonine, in terms of its IUPAC name, we call it your 2-amino 3-hydroxybutanoic acid. For your threonine, check the structure. How many chiral centers do we have? Class, may asterisk. Again, the asterisks denote the number of chiral center. So for your threonine, we have 2 chiral center. So therefore, how many stereoisomers does threonine have? Considering our formula for number of stereoisomers, 2 raised to n. Sir, direct plug-in lang yun, right? Yes, so the answer is 4 stereoisomers that also flashed here in our slides. Class, for your stereoisomers, they are actually enantiomeric pairs. See, 2R3R, its enantiomeric pair or the mirror image is the 2S3S. In terms of its structure, see, for your 2R3R, NH2 and OH at the right. For 2S3S, it's already at the left. That's why they are enantiomers. They are mirror images, They are mirror images of each other. Second example, 2R3S, right side the amino group, left side the amino group for our 2S. For our 3S, left side the hydroxyl, 3R, right side the hydroxyl. Class, remember, they always are mirror images of each other. So, sir, what is this typical type of visualization for enantiomers? Class, remember, this is your Fisher projection model, okay? This one, we have discussed this. What type of your structural representation? Line angle structure. Okay? So class, for enantiomers, we can actually use different 3D structures, flying wedge and Fisher projections. Class, ayan, this is just a supplementary discussion in order for me to introduce our configuration discussion, the assignment of R versus S configuration. Alright? Class, enantiomers, again, they can be represented using 3-dimensional structures like your flying wedge and Fisher projections. Check, this is through your ball and stick model, this is through your dash wedge line structure. Remember class, we will now use the 3D representation for the discussion on stereoisomerism. And in order to convert your dash wedge line to your Fisher projection, we actually use your flying wedge representation. See, we just rotated our substituents here in order to convert it to its Fisher counterpart. Don't worry, class, this does not appear naman in the board exam. So this is just a supplementary discussion. Ayan. Kaya pa ba? Class, you can take a break, ha? Again, you have the freedom to take breaks. So very important that you prevent oversaturation here in our discussion. But for me, I will now proceed with our next topic on our CIP priority rules. Remember, class, for CIP rules, this is very important in determining the R and S configuration of your organic compounds. Let's check, ha? Ayan. For your CIP, we also call it your Kahn-Ingold Prelog rules. So your R, it literally means right, and in Latin it is called rectus, or S sinister, which is literally translated to left. So meaning, if we have R configuration, it will rotate plane polarized light to the right. See, this is a clockwise direction. Alright? For your S configuration class, ayan, counterclockwise naman siya, again, to the left. Clear ba? Sir, what are the numbers here in our configuration discussion? Class, they have the priorities, okay? So first, substituent or functional group will be categorized based on our priority. Sir, how do we prioritize your substituents here? Based again on Kahn-Ingold Prelog rules. Let's first discuss the CIP rules. Again, we have a strategy in order to determine your prioritization. Check. Ayan, assign, compare, expand. ACE, diba? So again, first step, assign priorities by atomic number. I know you're familiar with this, but let's discuss. Look your atoms directly bonded to the chiral center. And remember, if your atoms have higher atomic number, that means we have higher priority. So usually, class, ang first priority are your halogens, diba? Because they have higher atomic number. Check. Here is our typical trend. Our highest priority, bromo. Least priority, hydrogen, diba? Here we have your bromochloro sonch. Ayan. So remember, class, bromine, because it has higher atomic number, usually it is highly prioritized. Okay? So again, that's the first step. Higher atomic number, higher priority. Alright? For the next step, step 2, compare. Particularly, compare your atoms if we have identical atoms. In particular, first thing to do, analyze the substituents. If you have identical atoms, Move to the next atoms outward, for instance, from the second atom to the third until you reach the first point of difference. O sir, what happens when we reach the first point of difference and then apply the first step or the first rule, higher priority ang higher atomic number? Sir, can you give an example? Let's see this one. For our alcohol and alkyl substituents, let's check. Remember, they are identical in terms of their C and their two H's. Ayan. So for the first 4 atoms, they are identical. Alright? I'm sorry, for the first 3 atoms rather. Sorry, again, 3 atoms. But when you reach the 4th atom, check oxygen for your alcohol, but hydrogen na po for your alkyl substituent. Which is prioritized? Oxygen or hydrogen? Sir, I know that's oxygen because it has higher priority or higher atomic number. That's correct analogy. So class, again, that's our compare step. Your step 2 in your assignment ng R and S configuration. And lastly, we have expand. In particularly, you need to expand your multiple bonds. When we say multiple bonds, these are your double or triple bonds. So usually, class, example, your carbonyl compound, we usually treat it as COO. Diba? Your double bonds will now be equal to 2 oxygen bonded to your compound. Okay? So class, later, we have an example for our CIP rule naming. So please revisit our discussion here. Again, straightforward CIP rules. You just really need to familiarize yourselves with our step-by-step configuration assignment. ACE, assign, compare, and expand. Okay? But for now, I will first discuss another type of stereoisomerism, your diastereomers. So let's check. For diastereomers, they are not simply mirror images of each other. Again, let's take threonine as an example. So what do we mean by diastereomers? When we say diastereomers, they only differ in one chiral or stereogenic center. So really, let's check. Let's double check here in our example. For instance, this pair, they are diastereomers because they only differ at their CYCLI configuration. Ayan. As you can see, right side is hydroxyl group for the 3R. But for this one, it is at the left for your 3S isomer. Alright? So again, they are diastereomers. Only differ in one stereogenic center. Next, for our next example, as you can see, both amino group at the left, but for your hydroxyl group, check, 3S yung isa, 3R yung isa. So again, their point of difference is only one stereogenic center. Class, please remember that. Again, in the board exam, your items might ask simple definition question like that. For the stereomers, again, they are only different in one chiral center or stereogenic center. I hope it's clear. In terms of the comparison of your enantiomers and your diastereomers, check their stark difference. For enantiomers, they are mirror images, di ba? Total, ayan, total change ng configuration. See, from RR, we switched it to SS. So they are enantiomeric pairs. For RS, sir, sabi mo switch. So again, yung R magiging S, si S, it will eventually become R to form your enantiomeric pairs. Remember, the definition of the stereomers, they only differ in one stereogenic center. For instance, between RR and SR, they are only different at the first stereogenic center. R for this one, and then S for our another. Okay, so again, that's it for your enantiomers and diastereomers. I hope it's clear again. Somehow they are related to each other. Sir, are there instances na may plane of symmetry tayo in our molecule? Yes. Okay, so we call those certain compounds as mesocompounds. Again, ang takeaway here, mesocompounds contain internal plane of symmetry. Okay, because the symmetry makes them identical, we call it your mesocompound. Sir, nasan dyan yung plane of symmetry? This one. As you can see, in this part may OH group, and in this part we also have OH group. And then, for both sides, meron din tayong carboxylic acid group. That's why meron siyang internal plane of symmetry. So you can further visualize this here in our Fisher projection. Diba? So you can see, class, we have your mesocompound here. Remember, this is an achiral molecule, despite they contain chiral centers. Alright? So here, typical enantiomeric forms, mirror images. Here, mesoform, they are actually identical because of the presence of your identical pairs of your mesoform. Class, please correct here, dapat this one is a COOH substituent. Alright? So class, that's it for our mesocompound. Okay, for our sample problem in our configuration assignment, let's check our sample problems here. Which group in each pair is assigned the higher priority? So step 1 class yan ha. First pair, CH3 or CH2, CH3. Sir, may similar atoms. Yung step 2, di ba? Compare. For your first substituent, the fourth or the main point of difference is in the fourth atom. For this one, hydrogen. For this one, carbon. So obviously, we will prioritize this one because carbon has a higher priority compared to your alkyl or your hydrogen substituents. Okay? Next set of pairs, iodine or bromine. Now, that's like your periodic table. In terms of their atomic number, which has a higher atomic number, again, that's your iodine atom. Diba? So we will prioritize this in terms of our R versus S configuration. Alright, lastly, ayan, we have CH2Br and we also have your CH2CH2Br. Class, remember, this one, we will prioritize this one. The main point of difference is your Br in this substituent. Here, ang counterpart niya is si carbon lang po. Okay? That's why we will prioritize this CH2Br substituents. Ayan, so I hope it's very clear na on your part in terms of our prioritization scheme. Let's check our next sample problems here. Rank the following groups in order of decreasing. Okay, class, again, decreasing priority. First one. Sir, I know we will prioritize oxygen because we prioritize your O atom. Class, again, this is our first, okay? First priority. What's next? So the next one, of course, is CnH2 class. Again, directly connected kasi with your nitrogen atom. So here is our second priority. And then third, very obvious na, or least priority, hydrogen. So this is the third priority. And lastly, C hydrogen atom. Clear? Next sample problem. This is our 4 sets of alkyl substituents and substituents. Let's see. Sir, I know si chlorine. Very evident, very obvious. Yes, because of its high atomic number. What's next? Okay, class, CH3 and CH2Cl, they have identical atoms, particularly the CH2 or the first three component atoms. Their first point of difference is between Cl and the fourth atom here is H. Between Cl and H, which has a higher priority? Of course, that's Cl. That's why, of course, this is your second priority. Okay? Class, again, first one, si Cl. Second, si CH2Cl. Thirdly, very obvious, CH3, and last pa lang po, si hydrogen. Ayan. So class, please remember, we prioritize your substituents based on the direct or the atom directly bonded to your carbon. Alright, for the last set of our sample problems, please answer this. Assign R or S configuration to the chiral center in the molecule below. Class, please pause the video before we reveal our answer here. Okay? So again, for our first compound, what is the first priority? Survey of used bromine. Alright, that's correct. This is our first priority. What's next? Again, CH3 and CH2. CH3, they have similar atoms na CH2. Their first point of difference, C and H. Between C and H, which is prioritized highly, of course, the C atom class. That's why this is the second priority. And then third one, palang si CH3. And then last po, si hydrogen. So class, check our rotation. So this is to the left, diba? So again, if it's to the left, R or S? Of course, obviously that's your S configuration. Class, this occurs because nasa out of the plane or your hydrogen recedes of our page. But if there are instances na your H carries the wedge structure instead of the dash, you will reverse the rotation. So instead of S, it will become R again kapag nasa unahan si H, or if this is your wedge structure like this one. Alright? So again, you will reverse the rotation. So eventually, it will carry the S configuration. But for our example, it's behind our page. Okay, on next example, please try answering, but for now, I will discuss the answer. Our priority atom, sir, yung S po, the sulfur atom. Yes, that's correct, diba? So again, this is our first priority. Next. Sir, I think the COOH because oxygen is highly prioritized. That's good. So thirdly, again, laging back burner si hydrogen. So we have here CH3 as our third group and fourth pa lang si hydrogen. Class R or S? Again, another S configuration molecule. So here, we have your S2 mercaptopropanoic acid. Ayan. So class, hopefully clear na sa inyo ang CIP rules natin ha. So now, we will proceed with our topic. Ayan class, kapit lang. We are now down with our last topic in our optical rotation experiment. So let's check ha. Ayan, for our determination ng optical rotation, particularly we subject here in our experiment your chiral compounds, because they are optically active, meaning they can rotate plane polarized light. Diba? So if the rotation is to the right again, dextro or the positive symbol. Okay? If it's to the left, levo. L for left, negative symbol. Okay? So what happens if in our mixture we have equal amounts of your dextro and levo compounds? Class, if that's the case, we have your racemic mixture. Okay, for your racemic mixture, the R mixture that contains equal amounts, so meaning 50-50 of your two enantiomeric forms, the or dextro and levo forms. So that's why optically inactive siya because it will just cancel out the rotation of your plane polarized light. Ayan. So usually class, this is done through polarimetry experiments. Diba? I emphasize this again through polarimetry experiments. So for our polarimeter, this is usually the polarization that occurs. Let's trace our mechanism here. If we have a light source, of course, there will be illumination of normal light. So in order to make a polarized light, very important that we have your polarizer. Diba? As you can see, upon reaching your sample, the light is already polarized. As you can see, it will be induced by your sample tube that contain a chiral compound. Of course, in the laboratory, we use polarimeter. Let's just watch this short video about our conventional polarimetry experiments. Class, this one will contain our sample chiral molecule. So this class, remember, calibration lang yan. Don't worry, it does not appear in the boards. But remember, much tedious ang process of the use of polarimetry or polarimeter using your traditional instrument. So later, we have a separate video for the modern instrumentation. Sorry ha, this specific information is not needed naman. Ayan, so let's just continue. Ayan, so that's it. You see, again, quantitative ang result for your polarimetry experiments. So class, again, that's just a supplementary video ha. So you don't need to remember the specifics of the steps in your polarimetry methodology. For now, let's proceed with our next video. Before I forget again, a polarimeter, it allows plane polarized light to travel through a sample tube that contains your chiral compound. So as you have seen in our previous slides again, after your light exits the sample tube, an analyzer slit will be rotated again the direction of your plane of the polarized light. Class, again, please check the previous slides na lang for our video discussion here. For the next video, check this is the modern instrumentation. Di ba class bongga, ang calibration here is already automated. Ayan. And of course, inside the equipment, the polarization occurs. And of course, the product here or result is also quantitative. As you can see here in our video. Alright, so class, that's it for our discussion on stereochemistry. Oh, sir, are we done? Yes. So now let's just summarize the important concepts in our stereochemistry discussion. Again, starting with your constitutional isomers. Remember, this is very specific in your different connectivity of your atoms, diba? Particularly the branching. For definition again, similar molecular formula, different connectivity. And ang consequences, it will give different physical and chemical properties of your isomers. As we have discussed, diba? If you increase the branching of your hydrocarbon chain or organic compounds in general, you will also decrease the boiling point. Ayan. So class, remember our discussion there, ha? Next, enantiomers, very fresh, non-superimposable mirror images of each other. For unique features, they have identical physical properties except for their capability to rotate plane polarized light or their optical rotation capability. Next, again, this one, they are only different in one stereogenic center. Diba? Sir, I know that eh. That's your diastereomers. Again, they also differ in physical and chemical properties. And remember, class, for diastereomerism, it's important that your compound must contain or must have two or more chiral centers. Ayan. And lastly, class mesa compounds, again, they also have chiral centers, but due to the presence of very symmetric functional groups because of the plane of symmetry, they are technically achiral. Ayan. That's why they are optically inactive. Class, let's just recall our 3D structural representations. Remember, we also discussed this in our discussion on Intro to Orchem. Now, firstly, we have your dash wedge line. Here's the structure of dash wedge line. Remember, this is particularly important for stereochemistry discussion. Next, Fisher projection, check. More on visualization of sugars and complex molecules. Class, remember, I emphasized the intersections here correspond to the chiral center. Okay? So again, it's like a fishbone structure, diba? Horizontal line, these are bonds directed toward the viewer. Meaning class, nasa front sila. In terms of the dash wedge line structure, they carry this structure. Ayan, wedge ang structure ng horizontal functional groups. For vertical lines, they are directed away from the viewer. So, that's the dash structure here in our Fisher projection. Okay? Ayan, thirdly, we have the Newman projection. See, this is another POV for our hydrocarbons. So, we view your compound through the CC bond axis. Ayan, protruding yung angle of our perspective. And here, class, it shows the free rotation of your CC single bond. Sir, what do we need to know here? Class, it's important to note here the different types of Newman projection. It can be eclipse, so meaning meron steric or staggered. Class, this is a typical sample of a staggered Newman projection. For the use or application, which for analysis ng steric interactions and conformations. Okay? So class, don't worry, hindi naman yung lumalabas sa port exam most frequently or frequently. Alright, for our next visualization, chair conformation. Diba? So class, this is very hard to draw. Relate? Remember, this is a 3D shape kasi. And for your Newman, remember, we have eclipse and staggered. For chair, we have your axial and equatorial positions. Okay? So class, we will discuss this as our topic on alkanes. But for now, again, this is very important for steric studies because here the axial and equatorial position will define the sterics that arises because of the positioning of our substituents. Okay, next visualization, sawhorse projection. Now, diba somehow, it's like your new projection but different angle. Side view na siya class again, tilted view to visualize the conformations. So similar with your Newman class, it has your staggered and eclipse conformation. So better lang yung angles natin here. And of course, very important to study the sterics through our sawhorse projection. Ayan. Thirdly, we have the Hayworth projection. So somehow this is partly a 3D structure, but the ring is flattened. So we highlight here kasi class the substituents positioning. It can either be above or below. So usually this is also used for stereochemistry. Clear? For our next two, we discussed this already. Ballistic model for our analysis ng bond angles and bond length. Particularly, our atoms here, they look like balls. Your bonds are sticks here. Ayan, diba? They are all color-coded by element. I know medyo advanced na to, but they are actually used in computational chemistry and analysis of your bond length. And lastly, space filling, the most accurate representation of our 3D structure because it shows the actual spacing of your atoms relative to each other. Class, again, this is great for studying the interactions of the several atoms in your compound. Ayan, class, lastly, finally, we arrive with our final last words for our discussion. Ayan, class, please try answering this one. So I will provide first the definition. This is a carbon atom bonded to 4 different groups such as your lactic acid. Sir, ang dali naman, that's just chiral center. Very good. Next. This contains at least one chiral center and no plane of symmetry. Still, chiral molecule yan class. Okay? So again, emphasis on the absence of plane of symmetry. Next, may contain chiral centers but has internal symmetry. Particularly, compounds. And generally class, umbrella term we use is a chiral molecule. Fourthly, non-superimposable, that's the two word, non-superimposable mirror images of each other. See, we have your SNR configurations, particularly that's your enantiomeric pairs. Third to the last, these are enantiomers that rotate light in opposite directions. For instance, we have your RS lactic acid. Again, these are your optically active enantiomers. And second to the last, it rotates light clockwise or positive, diba? Of course, that's your positive or your D or dextrorotatory enantiomers. And of course, if we have dextro, we have levo, and that's your negative enantiomers. All right, class. So to wrap up our discussion for this crash course, we will now discuss our quick quest. Ayan. So for our quick quest, this is a true or false statement. Let's see. Constitutional isomers have the same molecular formula but different connectivity. Sir, is that true? Yes, diba? We literally discussed that earlier. Again, they have same molecular condensed formula, but in terms of the branching or connectivity, they are somehow different. That's why true statement to class. Next. Enantiomers are superimposable. Class, again, this is the incorrect statement. So remember, enantiomers are non-superimposable mirror images of each other. So false statement 10 class, remember. Thirdly, a compound with no chiral center cannot have enantiomers. Yes, sir, because that is a requirement for a compound to be chiral. Correct. Remember? Ayan, this is a true statement because required na meron tayong chiral carbon in our structure. Class, hopefully you get it for this next item. Constitutional isomers have different physical and chemical properties, particularly with their melting and boiling point. Yes, sir, that's true. We discussed that in our discussion on Intro to Orchem. Yes, that's correct, class. Again, this is a true statement. Second to the last. Enantiomers always have completely different boiling points and melting points. Class, false. So I hope hindi kayo confused. This is a false statement. Again, they have identical physical properties and their point of difference, their ability to rotate your plane polarized light or the optical rotation characteristics of enantiomers. Diba? They have R and S configuration. Enantiomers have the same molecular formula and connectivity. No, again, they have different spatial arrangement. So this is obviously a false statement. All right. For our next topic, on our crash course 2, we have your reactions in organic chemistry. Class, this topic is very important for transition on our discussion of the different chemical reactivities of our functional groups. So here, we will enumerate the general features of organic reactions that you need to know and your classifications of our organic reactions. Additionally, we will also tackle your reaction mechanisms and the different species that you are expecting to see in our arrow pushing mechanisms. Particularly, that will include your electrophiles and nucleophiles. And lastly, we will also discuss the typical pericyclic reactions. So this one, class, this will only involve 3 different pericyclic reactions that are board exam relevant. Okay, so ready now with our next discussion, crash course 2, reactions in organic chemistry. Again, this is your 4 picks, 1 word here in our quick quest. Number 1, class, what is the common theme here in our 4 pictures? Of course, class, this is very easy. So this one is a chemical reaction, and this picture is a reaction mechanism. Diba? And these two, of course, they are reacting. Diba? They have reaction. So for our first common theme, ayan, remember, class, in our organic chemistry, this involves a lot of reaction. So some students raise concern because they are somehow intimidated with the sheer amount of reactions they need to study. But don't worry, class, we will discuss here in our crash courses the most important high-yield topics only. So that's in that case, we will prevent the overwhelming feeling. Okay, going back with our discussion. Next, for picture, 1 word item, C. Ayan, what is the common theme? Scientifically, the first and fourth picture, of course, that's an arrow pushing mechanism. As you can see, your nucleophile, or remember, nucleophile electron which will attack your or will obstruct a proton. Okay? Class, here, our main theme, as you can see, is attack. Ayan. So I hope you got the correct answer here. Remember, in our reaction mechanism, we always have nucleophilic attack because that species is an electron-rich compound. Alright, clear? Let's proceed with our next item here. Class, what is our common theme in our 4 pictures here? As you can see, we have what pictures here? That's our products. Diba? We have here our chemical products. And for our second and third picture, that is a particular type of reaction. We will produce 2 products each. Alright, so I hope it's clear again. For our last item in our minigame, this is the product. Recall, we have reaction, attack, and product. These 3 concepts are particularly related with our discussion this session. Okay, so let's start our formal discussion with the general features of your organic reaction. So here, we will just enumerate the important info that you need to know, particularly, class, the terminologies that you will frequently encounter in our discussion. Let's see. For our general features, first one, please guess, this is the starting materials or reactants that are transformed into new substances. So in any organic reactions, or in particular, your organic chemistry, we always involve the reactants or our initial substrates and your products that are generated through reacting your reactants. Okay? So again, for today's discussion, we'll break down what actually happens in your chemical reaction. So of course, we already seen reactants and products. Alright? So class, next. These are specific chemicals that initiate or speed up the reaction without being consumed. They can be classified as acids, bases, or metals. Class, what's the answer here? Again, it's in your manual. Your reagents, of course, this will initiate the reactions of your reactants. Well, particularly, we also have catalysts speeding up the reaction. All right? So remember, these first four features are the general features that we always see in any reactions in general. Not only in organic reactions, but in our chemical reactions in general. Next. Factors like temp or temperature, solvent, pressure, and catalysts affect the reaction rate and yield. Class, again, the role of your reactants, reagents, and this one, reaction conditions, will affect the spontaneity and the direction of your organic reactions. Okay? So later, we will also touch on some mechanisms and energy changes that happens during our organic reactions. But before we proceed on that, for our fourth general feature, this is the step-by-step, step-by-step pathway showing how bonds are broken and formed during the reaction. So we often involve here in this particular feature. This one, it starts with letter M. Check your manuals, class. Remember, these are your mechanisms, particularly reaction mechanisms. So in this feature, we always see the arrow pushing, diba? In order to track the flow of your electron from your reactants in order to produce our product. Class, our discussion here on the general features, particularly this overview, will help you better understand the logic behind our organic reaction. So remember, it's important here that you know the rationalization, not just memorization of our reaction. Alright, because this is something that we will use again and again, especially when we get to more complex topics in your alkenes, alkynes, and alkyl halides. Class, next set of our general features, reactions can be exothermic or wherein we will release or liberate energy. Or if we absorb energy, or if your reaction require an input of energy, we call it your endothermic process. So usually, class, for your catalysis, we always see activation energy. And this is the energy required in order to overcome our transition state that occurs in our typical chemical reactions. Remember, activation energy actually influences the speed of your reaction or our reaction rate. For this that's actually our energy changes. Plus, I would like to point out the very important info here, the term exothermic, the release or the liberation of energy. And the thermic, on the other hand, it's the input or the absorption of energy to forward our chemical reaction. So usually, class, your endothermic process are very vital for non-spontaneous reaction. Okay? I hope it's clear again, energy changes are important in order to predict the direction of our organic reactions, particularly to those reversible organic reactions. Alright, next, some reactions are reversible. Class, this is actually the answer already, the reversibility. Again, some reactions, they are reversible, meaning they can reach equilibrium at some point in our chemical reaction. But also, some reactions go to completion. So meaning they are irreversible somehow. Okay, remember, reversibility is very vital in your organic reactions in order to give way to your forward and reverse reactions in our organic compounds. So we will encounter frequently the reversibility feature of our organic reactions. But for now, class, please remember our reversibility feature. Alright, next we have this one. It determines which atoms or bonds react and how, diba? This one will include the discussion on radioselectivity, stereoselectivity, and chemoselectivity. So class, again, for organic reactions, particularly for our functional group reactivity, they are somehow selective and specific. So later we will discuss, because of this selectivity and specificity, we actually form a very specific product in terms of our configuration. Diba? From your stereoisomerism discussion, our configuration is actually specific with our organic reactions because of their inherent selectivity. Alright, again, please remember our 7 general features of our organic reactions. Class, these features are already given in your manual. So for our chem strategy in order to remember or study our concepts here are through active recall. So sir, is that through your flashcards? Yes, again, either digital or physical, class, it's really effective because passive reading will not really help you in retaining your relevant info. So class, please practice active recall. Okay, so for our next discussion, we will proceed with the different classifications of your reactions. So at this point, this is a preparation for our next discussions of your organic reactions. So usually, we classify your organic reactions based on the mechanism or the description of how reactions proceed. Alright, so let's first discuss the most prominent types of classification. First one, substitution, class, literally it just means that your one atom or a group of atoms. Okay, remember, it can either be single atom or a group of substituent or atoms in your molecule can be replaced by another single or group of atoms. So usually, class, we have two types here, SN1 and SN2. Familiar with these two types of substitution? We will actually discuss this in the types of your reaction for alkyl halides. Class, as a background, SN1 and SN2, these are nucleophilic substitution. So literally, we will substitute a new atom, particularly a nucleophilic group of atoms to our original substituent. See, for our first example, SN1, remember class, no need to worry with our specific mechanisms here. We will discuss the mechanisms on our comprehensive discussions of your reactions under alkyl halides. But for now, let's examine the example. See, we have here a chlorinated or chlorinated compound. Remember class, here we will substitute chlorine with a more nucleophilic substituent hydroxyl group. Alright, so again, keyword here, replace one group with another, usually a nucleophilic atom. Alright, so for our next example, SN2, your nucleophilic substitution 2, of course, here we have again an alkyl halide because of the presence of your halogen atom. So usually class, these two types of your substitution, they only differ in their reaction mechanism. For now, just absorb that we have these two types. Okay, again, similar mechanism. Substitute your iodine molecule here with a more nucleophilic substituent hydroxyl group. Alright, so class, usually we use another reagent in order to induce our substitution reaction. Again, substitution keyword, we replace your original reactant or substituent with another substituent that is more nucleophilic. Remember, your halides are good living group. Alright, so class, next type of our classification, we have addition. So usually this is prominent for your functional groups that are electron rich. Okay, so for addition, so very straightforward. This one we will add a similar or different molecule. So typically across our electron rich region. So sir, are double bonds and triple bonds electron rich? Yes, class. From our definition or discussion on your hybridization, they have pi bonds, and these pi bonds, they are rich in electrons. So they act as nucleophile and they will abstract a typical electrophilic substituent. Let's see for addition we have two main examples. Firstly, hydrogenation. Alright, so this particular reaction is a characteristic reaction of your alkenes and alkynes. So those compounds that have double and triple bonds. See, basic reaction lang to. Again, hydrogenation, we will add a hydrogen across our double bond. So here you can see we just added two hydrogens with respect to our two carbons. So class, this is a typical reactions again of your alkenes compound. Next, halogenation, similar with your hydrogenation, but instead of hydrogen addition, we will now add your bromine atom. Remember class, your bromine atom, it exists as an or as a diatomic molecule. So for our reaction mechanisms here, don't worry, we will discuss this in detail on your alkenes reactions. But for now, again, we will just add your bromine atom across our double bond. I'll check one for your one carbon here, and another bromine will be attached to our another carbon. Class, don't forget, our carbon is a strict follower of octet rule. That's why it's most stable if it has 8 valence electron across its bonding region. Clear for addition again, keyword, addition of a molecule, usually an electrophilic addition. Alright, so class, remember your double bonds and triple bonds are usually the one that initiates our addition reaction. Clear? Next, elimination. So somehow, elimination is related to our substitution. Sir, I barely remember that this type of reaction is also a characteristic reaction of alkyl halides. Yes, class, as you can see, we have two types, E1 and E2. So similar with your nucleophilic substitution 1 and 2, they only differ with their mechanisms. So class, for E1, E1 and E2, again, we mainly use your alkyl halides. See, again, this is an elimination, meaning we will eliminate your good living group here because your molecule is relatively stable upon, upon the elimination of your living groups. Particularly for our example, that's your bromine and chlorine atom. Because class, your halides, they prefer their anionic form, diba? Their bromide or chloride forms in which they carry a negative charge. Okay? So for elimination, as you can see, upon eliminating your halogens, we will form a double bond. Remember, strict follower si carbon ng octet rule. So usually we use here base in order to induce elimination. So strong base, your sodium hydroxide. So for your weak base, of course, we have your ethanol. Class, remember, we will discuss the specific mechanisms of substitution and elimination under our discussion of alkyl halides. Clear? Now, let's proceed with our next set of classifications. Redox, literally your reduction and oxidation. So for redox class, for our reduction, check. This one, literally, your compound will either gain hydrogen or lose oxygen. Remember that, that's our keyword. Again, for reduction, gain hydrogen, lose oxygen. And on the other hand, for oxidation, the opposite. Lose hydrogen, gain oxygen. So class, for the formal definition of redox, again, we will now involve the electron transfer among our organic compounds, where your oxidation and reduction are actually coupled with each other. Okay? So class, for redox, ayan, we have the coupling reaction of your reduction and oxidation. Let's see. For oxidation, as I have said, lose hydrogen, class, that literally happens or occurred here in our example. For your ethanol, or particularly in general for alcohol, upon oxidation, what is the function? Aldehyde if it's a primary alcohol. Class, again, for oxidation, it has the loss of hydrogen. As you can see here in our example. For reduction, again, your organic compound will gain hydrogen. Ayan, very evident with our example. For our redox, again, they are always coupled class. One is reduced and one is oxidized. Alright, so let's proceed with our next 5 classification. This one, you already encountered this in your Gen Chem discussion. For acid-base class, our keyword, proton transfer between your reactants. So this one, we have an acid and a base as our initial reactant. So usually class, for acid-base, this is a typical neutralization reaction. Because remember, it will just involve a proton transfer reaction. But here, our proton transfer, this one occurs through the proton transfer of your hydrochloric acid to your sodium hydroxide to form water and your salt as a byproduct. So class, this one is a pretty straightforward classification. Our keyword again is proton transfer, and this one occurs through your neutralization reaction. So I hope you are well familiar with this one because this is more relevant in your Gen Chem or Anachem discussion. Alright, let's proceed with our next reaction classification with rearrangement. Class, its formal description is when a molecule undergoes, again, rearrangement meaning structural reorg or reorganization. So usually class, we have a structural shift here in order to form a more stable product. So your rearrangement reaction, this occurs during the transition state. So if you have intermediates, it will form a more stable intermediate counterpart. So for instance, we have hydride shift in order to form a more stable carbocation. So sir, what do you mean stable? So class, remember, for stability of your carbocations, again, the most stable is the tertiary carbocation. That is the carbon that is directly bonded to 3 different carbons, as you can see here in our example. So class, again, for rearrangement, we prefer the production of a more stable carbocation. For instance, this is our initial intermediate. So remember, as you can see here, your carbocation is just actually a primary carbocation because it is just attached to a single carbon, as you can see here in our example. For your hydride shift in particular, your hydrogen will have a rearrangement shift to our original positively charged carbon. And our product, see, this is a tertiary carbon wherein it is attached directly to 3 different carbon-containing substituent. Alright, for our takeaway class rearrangement, structural shift in order to achieve stability. Okay, so again, we are concerned with a more stable form of our product. Alright, next classification, condensation. For condensation class, usually we lose a small molecule. Particularly, we have dehydration reaction. Here, we will liberate water molecule. Class, again, 2 molecules are required in order to condense or in order to proceed with our condensation reaction. So our byproduct here is a release of a typical small molecule, for instance, usually class water liberation or alcohol reduction. Sir, can you give an example of our condensation reaction? Class esterification. Okay, our ester functional groups are formed through esterification, reaction of your carboxylic acid with a typical alcohol. See, again, we will liberate water coming from your carboxylic acid and the hydrogen coming from your alcohol. Alright, so again, remember, with our ester, this is our carbonyl compound or carbonyl functional group, singly bonded carbon with your oxygen. And thus, don't forget, our byproduct, water. Clear, again, condensation, our takeaway, we lose a small molecule to join 2 molecules. Class, second to the last, here is a typical addition elimination. Sir, what do you mean addition elimination? Class, it is a simultaneous process. Again, simultaneous process wherein an electron-rich molecule, particularly a nucleophile, will attack a carbonyl carbon and then, consequently, it will be followed by elimination of a living group. So class, this is just an integrated type of classification. But for the specific mechanisms, addition and elimination, it's just similar with the mechanism we discussed earlier. So typical example of your addition coupled with elimination is acyl substitution. Okay? So class, firstly, usually, your nucleophile, particularly water, will attack your carbonyl carbon. So this one, it will form, a tetrahedral geometry. Again, for your tetrahedral geometry, we will form 4 single bonds. So this one, somehow, it will delocalize the double bond of the electron-rich regions. Okay? So after formation of your tetrahedral geometry, upon nucleophilic attack, your chlorine will be living. It will be eliminated because, class, remember, your halides are relatively good living group. And this one, of course, we will form your, what is this? a carboxylic acid molecule or functional group. So don't worry, class, if you are not somehow familiar with this, again, we will briefly touch this on our discussion on our typical carboxylic acid derivatives reaction. Okay? So class, again, for now absorb, we have a specific classification, addition, then consequently followed by elimination. All right? So for our next reaction type, we have pericyclic. So class, for pericyclic, usually, this one, we use two different molecules. So for instance, this one is a concerted reaction. So meaning simultaneous ang arrow pushing mechanisms between our two molecules. So again, this is a reaction that involves a concerted step wherein your electrons will move in a cyclic transition state. As you can see here, this one is a typical Diels-Idel or Diels-Alder reaction. Okay, so class, we will see this more on our discussions. But for now, again, let's just absorb that we have pericyclic, and our keyword here is the cyclic electron flow. Check with our generation of a and or a concerted reaction mechanism. As you can see, the electron transfer simultaneously occurs. All right, so that's it for our classifications of reactions. Remember, class, in general, we have 9 classifications that we will frequently encounter here in our discussion. Class, brief again, that's it for our reaction classification. Okay, so class, let's continue our discussion with our reaction mechanisms. Class, again, this is the bread and butter of your organic reactions because this one will allow us in order to track our electron flow upon reaction of your organic compounds. So to formally define, your reaction mechanism is a detailed step-by-step description of how a chemical reaction occurs at the molecular level. So class, here is a typical reaction mechanism diagram. Somehow it's overwhelming. So this one is very important in order to describe or define the speed of our reactions. Aside from that, of course, class, this one is very important in order to track where your reactants will go and what will be the products formed upon successful reaction. Or remember, your reaction, it can be a one-step reaction, and for this one, as you can see, it can also occur in a series of steps. Alright, so I hope it's clear. Again, this is a sequence of events. That's why it's a mechanism in order to track the flow of our electrons that participate in forming our new product. Alright, so class, let's see our typical component of your reaction mechanism. So remember, we usually see arrows, different types of arrows, in order to visualize our chemical reaction mechanism. So this one is very particular in order to trace our electrons, the formed intermediate species, the new bonds formed, and so on and so forth. So class, here are the typical arrows that we see in our mechanism or mechanistic diagram. So for these arrows, let's check their particular function. So as a general rule, of course, this is a reaction arrow that is irreversible. Class, again, for your one-sided reaction arrow, usually this is used for irreversible reaction. So how about the double reaction arrows? Class, these are your equilibrium arrows or those reactions that are reversible. It has a forward and reverse reactions. Okay? For double-headed arrow, this is usually seen for the resonance structure or for your compounds that are able to adapt to different predominant forms. So we will see this reaction arrow, the double-headed arrow, in particular in our discussion of tautomerism. Okay, but for now, again, we have 3 main types of our chemical reaction arrows: your general reaction arrow for reversible reactions, double reaction arrows, and finally double-headed arrows. Now, for our specific mechanisms, as you can see here, in red, we actually have your arrow pushing types of our arrow here. Class, for a full-headed arrow, as you can see, so mostly here in our examples, we have full-headed curved arrow. Usually this depicts that your electron, your lone pair of electron, will obstruct our particular site of reaction. For half-headed curved arrow, so usually class, for your radicals, if your reaction only use radicals or half of your lone pairs. Alright, so I hope it's clear. Again, we have your full-headed and half-headed curved arrow. So usually class, this one is seen on our typical radical reactions. Those reactions that include radical in its specific reaction mechanism. So class, remember, reaction mechanism, this involves formation of intermediates. So what are the intermediates here in your example? This one, inside our bracket. So usually class, as you can see, your intermediates can carry or can form or adapt to different resonance structure as depicted here with our double-headed arrow. Class, again, very important or crucial ang role ng ating intermediates. That's why we need to categorize our different types of intermediates. So again, this is usually seen in our transition state. They are usually produced in our transition states. Again, they are just temporary. They are occurring or they are produced between our starting materials or the final product. So class, our intermediates include your carbocation, the carbon ions, your free radicals, and other reactive entities. Okay? So again, your transition states are very rich in high energy, unstable arrangements that exist in your intermediates. Okay? So again, short-lived lang siya, class. When we say short-lived, temporarily. Okay? Temporary because it's formed in between the steps of our reaction. Let's see our typical intermediates here. So you can see, we have seen this earlier in our rearrangement. Diba? Carbocation, literally class, that's your intermediate that carries a positively charged carbon. So in general, your carbon will carry positive charge. So here, our stabilizing factors involve the inductive effects. So that's through our sigma bonds, hyperconjugation, particularly if you have double bonds present in your structure, and resonance. So similar with hyperconjugation, if you have a double bond, not necessarily just alkenes, but generally double bond present in our organic compound. So class, the stability of this intermediate should be a big role really in determining whether a reaction will form a stable product or they will proceed smoothly or it will rearrange. Okay? Again, for instance, we have your nucleophilic substitution, elimination, and rearrangements. Plus, again, carbocation keyword, positively charged carbon. All right? So again, think of it as a carbon desperately seeking electrons. Okay? Next, we have your carbon ion intermediate. So if you have a positively charged carbon intermediate, of course, the opposite is negatively charged carbon. So usually the stabilizing factors are just similar. Resonance and inductive effects, particularly if you have electron withdrawing substituents. So those that are particularly electronegative. For instance, halogen class. Okay? So again, we will usually see carbon ion in our nucleophilic additions or your reactions that will involve base reactions. Okay, so again, that's it for our carb and ion. Remember, this is your carbon with extra electrons. So usually they are ready to donate these electrons or they are ready to abstract or get a proton. Okay, class. So our next intermediate, of course, free radical. So again, they have one unpaired electron in its structure. So class, this is actually a neutral compound, but its unique characteristic is the unpaired electron. So similar stability factors, hyperconjugation, particularly in your double bonded organic compounds, and resonance. So for instance, with our allylic and benzylic radicals. So don't worry, we will encounter these two types of radicals. So usually your free radicals are formed through polymerization of your alkenes or halogenation of your alkanes. Class, again, your free radical substitution, as you are familiar with it, it is a characteristic reaction of our alkanes. Remember, usually or relatively unreactive ang alkane. So, it only reacts through the production of your free radicals induced or produced by light, okay? Light absorption. Alright, so lastly, carbene. Class, this is a typical structure of your carbene. So, similar with free radical, neutral, but here, your carbon will now carry two non-bonded electrons. So that's why we call it your divalent carbon because it has one lone pair or two non-bonded electron. So usually, ang stability factors natin occurs in our singlet or triplet form. So that's with respect with our bonding, okay? Or substituent effect. So usually, if you have electron donating, of course, or electron withdrawing, it will affect the capability of your carbene to react or to abstract a typical substituent. Alright, so class, remember, this is a neutral carbon that, well, it acts strangely because it has two bonds with your hydrogen and two non-bonded electrons. So typical reactions that involve carbene, cyclopropanation of your alkene or insertion reaction. So meaning it can insert itself into other bonds or through cyclopropanation, it can create small rings like your cyclopropane. But for now, again, class, please remember our four main intermediates: carbon ion, free radical, and carbene. For free radical and carbene, they are neutral compounds. They only differ with the number of the non-bonded electrons in their structure. Alright, so remember intermediates are in your transition state. So with that, your transition states again, class, our intermediates, they have high energy and unstable sila, meaning they are highly active towards the formation of your more stable product. So that's why this one is temporary lang, okay? Again, this is the process wherein our bonds, your all bonds will break and your new bonds will form. So from your FEChem, di ba? This is a typical reaction coordinate. Your transition state is the highest, okay? The highest point in our Gibbs free energy and reaction coordinate graph. Okay, so class, remember, this is where your intermediates can be found. Your transition states are where your intermediates, your high energy unstable species were produced. Alright, so please remember that for reaction mechanisms, we discussed the different arrows or the components of your reaction mechanisms. Second, the intermediates. And thirdly, the transition states where your intermediates are found. Okay, so our last topic for our discussion, of course, is on your electrophiles and nucleophiles. Let's see. For electrophile, literally electrophile, it is electron loving because it is electron poor. Thus, it loves electron. It wants or it accepts an electron pair in order to form a bond. On the other hand, for your nucleophile, again, it is an electron rich. So, of course, it will donate your pair of electrons in order to initiate the formation of your new covalent bond. So, class, in every reaction, we have your electrophile and nucleophile. For electrophile, again, electron poor. For nucleophile, electron rich. Or let's take this reaction as an example here, which is the electron rich. So sir, again, because it's electron rich, that's the nucleophile. Yes, so usually that's the compound that has a double bond. So class, remember, our initiator of your attack is always your nucleophile because they are the ones that are electron rich. Okay, so typically your electron rich molecule will initiate attack to your electron poor in order to form a covalent bond. So for our particular example, typical reaction of alkenes is to react through electrophilic addition because of the reactivity of your double bond due to its electron rich nature. Next. For our next sample, ayan, we have your class. This is the symbol of your nucleophile, ha? So again, electron rich yan. And it will abstract, okay? It will attack your electron poor molecule. So for instance, usually we have alkyl halides. Remember, good living group, ang ating chlorine atom or in general your halide because they are stable in their negatively charged form. Alright, so remember, these are the two types of our mechanistic overview of your electrophiles and nucleophiles. Ayan, so class, as a summary, this table is already in your manual. So remember, for electrophiles, for straightforward definition, electron loving. So they are electron deficient, nucleophiles, electron rich. For our tip, usually class, ang electrophiles, they are positive or partially positive. O see, hydrogen. You also have your NO2 plus and your, ayan, boron, trifluoride. Okay, so class, please remember our common examples. For nucleophiles, we have your negatively charged compounds or they have lone pairs or pi bonds in their structure. So usually kasi yung pi bonds class, they are electron rich, very rich in your electrons. Okay, for electron flow again, your electrophiles will always be the one to be attacked because they will accept electrons coming from your nucleophiles. And for your nucleophiles, similarly, again, that's the source of your electron as they will donate those extra electrons from their structure. Okay, so class, again, they are attracted to each other. You can see they are complementary. You have electron poor and electron rich compounds. Okay, so class, again, don't forget our particular common examples here. Again, we discussed our example reactions and for the patterns and common reactions. So usually naman, this is just supplementary. So I will give you this one as a reading assignment. Okay, clear ba? Because for the identifying patterns, sorry, this is just similar with our charges, diba? So again, positive, so meaning incomplete yung octet, and highly polarized ang bonds. That's why it has a positive or partially positive charge. So the opposite is true for your nucleophiles. Electron rich dapat, so it has an extra electron. Negative siya or partially negative because of the presence of your lone pairs. And class, remember again, pi bonds are electron rich. Okay, so class, for our last topic pa pala, for our discussion on your reactions in ORCAM, we have this particular classification of reactions that we have seen earlier. Remember, this is also a board exam relevant topic. So for pericyclic reactions, again, our keyword here is the concerted reaction, wherein we have a cyclic transition state. So usually, we have or we need an input of heat or light in order to induce or to start our reaction. So class, remember, each stereoisomer of the reactant here will yield a specific stereoisomer of your product. So sir, simply, they are or these reactions are specific. Yes, remember, it has its own specificity and selectivity in terms of the formation of your transition state. That's why it is stereoisomer specific. So for pericyclic reaction class, we actually have three relevant examples or classifications. Let's start with the first one. This one is very easy, your electrocyclic ring opening or ring closure. So this one is a reversible reaction, and again, it will involve the closure or opening of our ring or cyclic ring structure. So usually this is induced by heat. So class, straightforward lang yan. And again, the reaction mechanism, as you can see here, is a concerted process, wherein for your electrocyclic ring closure, our source of your electrons will be the double bond conjugation in our compound or reactant, our initial reactant. See class, your arrow pushing mechanism or the electron transfer process occurs in a concerted process in order to form this product. See, very easy. Again, for ring closure, this is our typical mechanism. So again, class, towards a more stable product tayo for your pericyclic reactions. So that's why, for ring opening, usually class, sterically hindered ang mga products or sorry, reactants that undergo ring opening. For instance, you have your cyclobutene compound. So this is very sterically hindered. That's why, with the introduction of heat, we will form its open or a cyclic structure. Okay, so again, concerted process of your electron transfer. So first one, your electron-rich double bond will initiate the electron transfer that will, okay, that will result to your ring opening. So remember, this is a reversible reaction, but of course, we favor the formation of a more stable product. Clear. Next, we have class. What is this? Your famous Diels-Alder reaction. So here for Diels-Alder, we have your diene. So again, two double bonds and your dienophile. So again, concerted ang reaction mechanism natin here. And particularly, Diels-Alder reaction is a type of acycloaddition reaction. And for this reaction, our unique feature is the reaction between your two compounds. Both have pi bonds that will form eventually a one cyclic product. So sir, what's the conversion here? Again, pi bonds will be broken to form two new sigma bonds. See again, with our diene and dienophile, we will form particularly a cyclohexene product. So again, class, you need an input of heat or light in order to induce pericyclic reaction. So don't forget Diels-Alder reaction. This is a type of cycloaddition reaction. So this one is particular with your 4+2 reaction. So this is a 4-carbon diene with your 2-carbon diene, and of course, they have the presence of double bond. So class, remember they have 4 pi electrons as well. As you can see here, ayan, the 2 pi electrons and another 2 pi electrons. And another one for the dienophile. Again, for your double bond recall, we have 2 pi electrons coming from your 1 pi bond. So particularly here in our example, our product is a cyclohexene product. So again, class, for the 4+2 reaction, that's specific for your Diels-Alder reaction. Okay, for carbon plus 2 carbon, of course, they have 4 pi electrons with your 2 pi electrons coming from your diene and dienophile respectively. But don't worry, later we will have a sample problem on your pericyclic reaction. But for now, let's discuss our third type, your sigmatropic rearrangement. In particular, we have here the formation of your 3,3 sigmatropic product. Ayan. So for your sigmatropic rearrangement, so if you have your pi bonds, okay, pi bonds being broken for cycloaddition, here we have a migration through our sigma bonds. Let's read. Sigmatropic rearrangement is a reaction in which a sigma bonded group will migrate across your pi electron system that will result to the breakage or the cleavage of your one sigma bond, shifting your pi bonds, and therefore it will form a new sigma bond. Class, let's discuss that slowly. Again, your sigma bond group will migrate across a pi electron. Sir, where is that particular sigma bond? Class, that's in your 1,1 atom. Okay, again, that's your 1,2 carbons. So with that being said, because of your migration across your pi electron system, oh sir, wait, where's your pi electron system here? Class, this is your double bonds in the structure. So because of the concerted electron transfer, as you can see, your electrons here will be transferred here. That's why we will form a new double bond. And then of course, this bond will migrate to this bond to form your pi bond. And this bond will form a new sigma bond here in our 3,3 labeled carbon. Okay, so usually class, our specific or prominent type of sigmatropic rearrangement is your 3,3 sigmatropic rearrangement. Particularly, we have two subclassifications. We have your Claisen and cope rearrangement. These two are actually board exam relevant type of sigmatropic rearrangement. Okay, so first we have your two types again, your cope and Claisen rearrangement. So in particular, for cope rearrangement, of course, this will always involve your 1,5 die-in. So class, again, for your 1,5 die-in, your sigma bonds here, will migrate through our pi electron system in order to form at least 3 new sigma bonds. So for our product, ayan, you have the new 3,3 sigma bond here in your isomeric 1,5 die-in because your double bond also migrated from our 1,5 die-in to your isomeric 1,5 die-in. So for Claisen rearrangement, we have an allylic vinylic ether. So when we say allylic vinylic, your ether, particularly your oxygen, the carbon that is bonded directly to oxygen is analylic, meaning it is connected to your double bond, and vinylic on the other side because it is directly participating in your double bond formation. So of course, similar strategy class, this is your 1-to-1 bond, so it will migrate through your electron transfer process. So this one will migrate here, this one will transfer here, and this one will transfer here. So that's why our product, of course, ayan, obviously an unsaturated aldehyde. Remember, this functional group is an aldehyde functional group. So as you can see, both of these two sigmatropic rearrangement, they proceed through a 6-member cyclic transition state. And of course, your cope rearrangement class in particular is a reversible reaction, as you can see in our reaction arrow. And particularly, this is for your 1,5 die-in exclusively. For your Claisen rearrangement, check the reaction arrows, an irreversible reaction for your allyl vinyl ethers. So usually we will form a new new pi bond between your carbon and oxygen. And here in your aldehyde functional group. See again our specific arrow pushing mechanism here. Your sigma bonds at the 1-1 position will migrate through our pi bonds electron transfer in order to produce a new sigma bond here. Diba? Again, don't forget the breakage or the cleavage of your sigma bond in our 1-1 position. So sir, what is the cyclic transition state here? Ayan, so as you can see, it's a 6-membered ring for our cyclic transition state. And therefore, afterwards, ayan, you will form your unsaturated ketone for this particular example because we have a substituent here in our formation. Clear? Class, let's try answering our sample problems here. So for our pericyclic reactions, we have again 3 types. Your electrocyclic reactions, cycloaddition reactions, and your sigmatropic rearrangement. Class, please try answering our sample problems, but for now, I will discuss the answer. The first one is a type of your Diels-Alder reaction, a cyclic or cycloaddition reaction. So remember, our arrow pushing mechanism here, of course, is the electron transfer between your die-in and dienophile. Class, sorry for my arrows. Again, so of course, because of your electron transfer, our product here will be the formation of your cyclic ring structure, particularly with your cyanide in our substituent. Okay, so this is very easy. Next one, for our next sample problem, this is a sigmatropic rearrangement, a 3-3 sigmatropic rearrangement. So again, with our arrow pushing, we will start here, and then this one will migrate here with your sigma bond, it will break or it will be cleaved, and then this one will form your new sigma bond here to form our 3-3 sigmatropic product. Clear? Again, this is our particular arrow pushing mechanism, and this is our product. Ayan. So class, remember, first sample problem, cycloaddition reaction. Second is with your sigmatropic rearrangement. Ayan. Okay, so class, we are done with our discussions on your reactions in organic chemistry. So as a recap, class, please remember the important concepts that we tackled here initially with our general features. Remember, this one involves your reactants, reagents, and specific conditions in order to proceed with our chemical reactions. Particularly, class, it has your specific optimum temperature, pressure, and correct solvent.